In this video series, we'll be taking a look at the C Preprocessor and the features it provides. To start, we'll provide an overview of what the C Preprocessor is, and then move on to our first directive, #define. Often when we are speaking colloquially about the process of transforming our source code into an executable file, we say that we are passing those source files directly to our compiler, and the compiler produces an executable file as its output. This, however, is an oversimplification that ignores the role of the preprocessor, assembler, and linker in producing an executable file. When you build a C program, your source files are not given directly to the C compiler. Instead, they're given to a preprocessor, which then passes a modified version of those files to the compiler. We can control which types of modifications take place by using preprocessor directives. Each preprocessor directive starts with a # followed by a keyword. The best way to get an understanding of how these directives work is by comparing the output of the preprocessor to the original C source file. So let's do that. On the left I have my C source file, and on the right is a live preview of the output of the preprocessor. The first thing to notice as I start writing a C program here is that if I'm not using any preprocessor directives, the output from the preprocessor will be the same as what I had in my original source file, with the exception of small changes in formatting that have no impact on the behavior of the program. Also, if I write any comments, those will be stripped away by the preprocessor. The #define directive can be used in a few different ways. The most basic is for defining constants in a program. To do so, you must write #define, then the name of the constant, followed by its value. You can use either upper or lowercase letters when defining the name of a constant. However, by convention, we typically use all uppercase letters when defining constants so that they are visually distinct from variable names. Here we have defined a constant called buffer size that is being used in multiple locations. In each location, the preprocessor replaces the name of the constant with the value it represents. If we change the value of the constant, that change will automatically be applied everywhere the constant is used. The preprocessor also lets us define new constants based on old constants. In this example, address space size is defined as 1 left shift bit width. If we define bit width to be 5, we see the output from the preprocessor becomes 1 left shift 5. This will later become simplified to 32 by the compiler. If you have prior experience using the C preprocessor, you might notice that I am doing something very dangerous here by not including a set of parentheses in the definition of address space size. We'll come back to this in a little bit. The second way in which we can use the #define directive is for creating parameterized macros. In this example, we have a parameterized macro called area of circle. In this usage of the macro, we see the parameter r is replaced with the value 10. Again, I'm doing something dangerous here by not using a set of parentheses. We'll come back to that later. But first, let's answer another question. Why would I use a parameterized macro when I could accomplish the same thing using a function? I could choose to define a function called area of circle and make a function call here instead of using the parameterized macro. In either case, our area variable will end up containing the value 100 pi. The difference is in when this computation happens. In the parameterized macro example, the compiler will see the expression 3.14 times 10 times 10. This makes it possible for the compiler to evaluate this expression once at compile time, so it doesn't need to be re-evaluated every time the program runs. In the function call example, the compiler only sees a function call is being made, and therefore this optimization cannot take place unless inline functions or aggressive compiler optimization settings are used. Here we have another example where we have a parameterized macro and a function that will both return the square of a number. At first glance, we might assume that both of these would produce the same result. However, this is not the case. If we run this code, we see the value of a appears to have been incremented twice, and the result of the parameterized macro appears to be 2 times 3 instead of 2 times 2. If we look at our preprocessor output, we see that the square macro produces a++ times a++, which means the value of a will be incremented twice, and the result is going to be 2 times 3, just like we saw. With the function call, b is only incremented one time. If you want to avoid this potentially unexpected behavior, it's best to only call parameterized macros with expressions that do not produce side effects. The other major source of unexpected behavior from parameterized macros comes from not using enough parentheses. Here we have 4 different versions of a parameterized macro for calculating the sum of two numbers. In our main function, we're using all 4 to calculate the sum of 2 plus 2, which we would expect to be 5. When we run this program, we see all 4 macros work as expected. But now let's suppose we want to multiply this sum by 2. We'd expect to get 10 in all 4 cases. Let's see what happens. The first and third macros do not produce the correct result. Let's take a look at the preprocessor output. In the first version, we see the macro produces 2 plus 3 and it's followed by times 2. But because multiplication has a higher precedence than addition, 3 times 2 will be calculated before the addition takes place, and therefore we get an incorrect result of 8. Version 3 suffers the same problem. With versions 2 and 4, this extra set of parentheses surrounding the entire macro definition ensures that the addition takes place before the multiplication. It is good practice to surround all of your macro definitions with a set of parentheses to avoid this problem. Now let's suppose we want to left shift the value of 2 by 1 before performing the sum. If we left shift 2 by 1, that would give us 4, and then adding 3 would give us a final result of 7. When we run this, we see the first 2 macros fail to produce the correct result. Let's take a look at the preprocessor output. The first macro produces 2 left shift 1 plus 3, but because of the order of operations, 1 plus 3 will be evaluated first instead of 2 left shift 1. Therefore, we produce an incorrect result of 32. Version 2 suffers the same problem. Versions 3 and 4 are immune to this issue because of the set of parentheses wrapping around the argument containing the left shift. It is good practice to surround each argument inside your macro definitions with a set of parentheses to avoid this problem. Since version 3 is the only macro that both wraps each of its arguments and the entire expression in sets of parentheses, it is the only one that is guaranteed to be safe from this class of operator precedence bugs. Check out the playlist in the video description to learn more about the preprocessor, or this video which covers the #include directive. You could also subscribe if you'd like to learn more about C, assembly, operating systems, and other aspects of low-level programming.